Hello, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video, we're going to go over the radical reaction mechanism. In particular, we're going to go over the substitution radical reaction. We're going to learn about its general mechanism. We're going to learn about the energy diagram. We're also going to learn about the energetics, the changes in energy that take place during this reaction. Okay, so let's get started. The first thing I want to talk about is the mechanism. Now, you could see it typed out here because I use this mechanism several times over in this video. So instead of writing it over and over, I have it typed out for me. But I do strongly recommend that you write this mechanism out because you really have to understand how to do it by hand from scratch for yourself, okay? So during your exam, you're expected that you're going to see something related to this, okay? So make sure to write this one out and get used to doing that. We'll also do problems, obviously, that will carry you along as well to get mastery of this. So the first thing I want to talk about is the general mechanism. Now this is called the substitution. This is a radical substitution reaction. And the reason why is because, as we know from a general idea of a substitution, we're going to swap pieces out from two different molecules. We're going to substitute, right? So in this case, we have a carbon with 4 H's and a Cl2. At the end, the carbon is going to swap one of its H's out for a Cl, and the Cl2 is going to lose a Cl for an H. So we wind up getting that right there in an HCl. So that's our substitution. Now, this requires a hydrocarbon, like an alkane, and for now we'll talk just about alkanes, and also some sort of halogen. Now, the way it works is the very first step is what's known as the initiation. And the I'll write I-N-I, or initiation, or just I, right? All mean the same thing. Now, initiation is required because, remember, it's very hard to make radicals because it's just not a very stable thing to create. So it's not energetically favored. And so in order to get this to go, in order to get this reaction to occur, you need to initiate it with a radical initiator. Okay? And we saw a few of them in the previous video. In this case, we're using the halogen that we want to do the substitution with. So we're going to use Cl2. Well, in order to get the Cl's to break apart, now remember, Cl's are high, they have rich electron source around them. They have 3 pairs each, and that's already creating a resistance between those two atoms, right? But we need something to kick it off, and that's what the heat is for. Or we could use light. Either one. It's going to provide energy, whether it's heat or thermal energy, or we use light to get the energy. Either way, we're going to allow this radical to break apart, or this Cl2 to break apart and become radical. Now remember, the way we illustrate radical is by a fish hook arrow. So I can do it like that, and that's one way, just to show one up, one down, and going towards the halogen, and now I have 2 radicals. Once you go through initiation, now these radicals are bouncing around in space, and the reaction actually begins. So now we're going to start doing what the next step is, and that's known as a propagation. This is called a propagation, or it's known as P1. That's how I write it, P1. Propagation 1 is where our newly formed radical, the Cl, is going to bounce around and it's going to hit an alkane, in our case, methane. So when this collides, because of how reactive they are, whatever they hit, they wind up bonding to. So if you could imagine, if we have a methane, think of methane, it's shielded all the way around, all 4 points around it are hydrogen. So if something is going to collide into it, a radical, the first thing it's going to hit is a hydrogen, right? And so when it hits that hydrogen, so when this comes and collides with the hydrogen transfers its electron over to it and makes a bond. So now we have an HCl. But the carbon that held the hydrogen, it winds up becoming a radical because the hydrogen detaches from it, right? The hydrogen leaves with its 1 electron. And so we wind up making a carbon radical. So we make one of our 2 products in propagation 1, and now what we're going to do is we're going to take our newly formed radical, it's always the same procedure, we take this one now and we drop it down into the next equation step. So notice how we're writing this out. We write it in a more linear fashion. It's not like one straight reaction. There's steps. There's sub-reactions that are going on. So we're going to go to P2 now, propagation 2, where we start with the radical that we just created, the alkyl radical, and now it's going to collide with a halogen, a Cl2. Now you might say, well, in the first step, didn't we make radical CLs? We did, but you have to remember there's millions and millions of these, right? So they're not all going to become radical. Some will, maybe even a very little bit will, but the rest of them are going to stay as neutral molecule. So there are Cl2s for sure because they don't all become radical. Remember, radical formation is a very difficult thing to do because they're so unstable radicals. So it's going to resist that type of breakage. And so we will have Cl2, and what this is going to do is it's going to collide with one of the Cl2s while a Cl makes a radical to it and the other Cl becomes a radical. So now we have our second product. We have our alkyl chloride in propagation 2, and in propagation 1, we made our hydrogen chloride, right? So we had HCl and methyl chloride. And we also made a radical. Now what's going to happen? Well, propagation is going to keep going on. So this right here, Cl radical, is now going to go back up to propagation 1 and react with another alkane. So this keeps happening over and over and over again. So think about it like dominoes. If your finger is the radical initiator, if you have a bunch of dominoes lined up and you push the first one, they all go. This is known as a chain reaction. So this is a radical chain reaction. Why? Because as soon as you make P2, you've created what you need for P1. So it just goes and hits another alkane and becomes HCl again. And then that alkyl radical becomes the P2 reactant side, right? And then it goes and hits a Cl2. And this keeps happening over and over and over again. As a matter of fact, you really can't control this very well. In a lab, once you get this thing going, you just wait patiently for it to stop. Now, there are techniques and tricks that I'll explain to you in a moment that you could do to try to get it to stop, but it's really hard to stop a radical reaction. It's something that's just going to keep happening until it runs out of all possibilities, okay? Eventually, as you let this thing go long enough, you start to build up the amount of radicals in the environment. Because remember, there's many happening at the same time. So some radicals are around and they didn't connect with anyone yet, right? So as time goes by, you'll have a larger concentration of radical in there, and eventually radicals will start to find each other. When two radicals collide, that's called termination. So it doesn't matter what the two radicals are, but if two radicals come together, that is known as termination. And that's the last step here, T, termination. Now, in my termination example, I'm showing you the opposite of initiation. So notice how above in initiation we made two radical chlorines? Well, now we're colliding them back together. So eventually these Cls will find each other, radicals, and they collide. When radicals collide, they don't make new radicals anymore. So that's why it's terminating. If every radical hit another radical, then the reaction's finished. Okay? But I just want you to recognize that for termination, there's more than just what I'm illustrating. If you look at any two radicals that you created above in propagation 1 or 2, they can collide together. So you can have, for example, a methyl radical collide with a Cl radical, make methyl chloride, or a methyl radical and a methyl radical collide to make ethane, right? So that can happen. Any two radicals that you create can collide together. Now, here's the thing. There are certain things that are more likely to happen than others, and we could figure that out in the next section. But for now, I just want you to know they all can and will happen. So these things will happen. There's a reason why I picked the two halogens coming back together. You'll see that also in our next section. But everything can happen. Any two radicals can come together. And furthermore, not only do two radicals come together, but let's say you make an ethane. There's nothing stopping a radical from hitting that, and now ethane becomes a radical. And then it bounces around. So you get things in this that you wouldn't even imagine. Like you get hydrocarbon. You started with methane. You might have 5 carbons long as a product. So you get, because you just keep building it up.